Hi, it's Robin. On Twitter, I follow Dataram 57, and I noticed this tweet from him. It's about a month old now. It's taken me a while to get to it. He issued a challenge to mathematicians and programmers to try writing an equation that will display this pattern. I'm showing you his tweet here. Looks pretty simple, but he wants you to do it without using any ifs. So how do you generate a display or an animation like this without using if? So since I had my VIC-20 out still, I want to try using this computer to solve this problem. But because the size of the display is 90 by 80 in the challenge, that doesn't fit in with the VIC-20's normal 22 by 23 character array. It doesn't have any built-in high-res graphics. But then I remembered that I have the Super Expander cartridge here, and this adds both 3K, a whole 3K of RAM to the VIC-20, but also a number of extra basic commands, and that includes some high-res or simulated high-res commands for drawing a bitmap screen. So this is the original cartridge, but actually that new Penultimate Plus cartridge that I got a while ago, I was showing you a couple episodes ago, it actually has this built in too. So I'll just show you that. We'll start it up here in this main menu. It's got all kinds of stuff, but here under Utilities is the Super Expander plus 3K, and then I think this one's been modified so you get 27K of RAM and the Super Expander, but we'll stick with the classic one. That's all we need today. So I think first, just to get the hang of this cartridge and the graphic commands, we'll try solving this with an if statement or two, because I suspect that should be easier to do, and it'll let us test out the bitmap mode first. So I've written a little program just to do exactly that. So for the width, I'm going to put 89. The width is 90 pixels, but we're going to be zero based here. From 0 through 89 are the valid positions. So I'm just going to say the width is 89. It just saves us having to subtract 1 in some calculations. And the height, likewise, is going to be 1 less, 79. And we'll just initialize t to 0. T is time step, and that's going to be what drives this animation. We're going to keep incrementing time by 1, and the animation will display. Okay, we'll need some more variables here, like the X position that we'll call it the cursor, the dot, is currently at. And also Y. We're going to start it up in the top left corner like the animation. And then for this version, we're going to do a delta X of 1 and a delta Y of 1. As the dot moves through the animation, each time step, that's going to be the speed that steps. That's going to step 1 pixel in the X, that's the delta X, and 1 in the Y. Actually, this reminds me a lot of the VIC-20 manual that came with the computer. There's this bouncing ball animation down on page 64. That's a nice number. Here's a short program to bounce a ball around the screen, followed by a detailed explanation. And you see here it's actually using the same X, Y, delta X, delta Y, and making the ball animate. So you may have typed that program in if you had a VIC-20, or a C64 actually has a similar program in the C64 user's guide. Okay, and now we're going to set graphic to 2. Now this is one of the extra super expanded instructions that the VIC-20 gets from this cartridge. This sets the high-res bitmap mode. And according to the manual here, graphic 0 is for the normal text mode, graphic 1 is for multicolor mode, and 2 is for high-resolution mode, so that's what we'll be using here. Note that the VIC doesn't actually have high-res graphics, but it does have redefinable characters, and that's what it's using here. It's using the character set as a virtual bitmap mode. Okay, and another new command is point, the color number 1, and then X comma Y. So that's just going to draw a pixel on the screen at our current point. Now we're going to update X by delta X and Y. So that's moving that point by 1 step down and to the right. Now we're going to check for collision with the edges. So if x is equal to 0, that would be the left edge. We're not going to get there for a while. Or if x is equal to the width, then dx equals negative dx. So it's like a collision with either the left or the right edge of the screen. Then we flip delta x, so it'll go all the way to the right edge of the screen, and then it'll flip and become negative, so it starts heading the other direction again. And then we can just use the same. We'll flip this around. If y is 0 or y equals the height, then dy equals negative delta y. 80, and then we'll go to 40. Okay, so that's our program. Let's give it a run. Okay, it's working, but it's really small. So what's going on there? Well, sort of strangely, this virtual bitmap has a virtual resolution of 1024 by 1024 pixels, but the VIC doesn't actually display anywhere near 1024 pixels. So we can just add a couple lines to scale that up. We're just going to add line 25, a scale of 11.5, and that's just a variable s that we're using. And what that is approximately the 1024 virtual pixels by the width that we're using of 90. That comes out, wow, pretty close. 11.37. Should I do that instead? And then here, where we're actually applying the point, we're just going to multiply that by s. So it's scaled up, and we'll try running that. And there we go. I suppose we could use a different scale factor in the y dimension. Sure. Scale of x and scale of y. Current 1024 divided by 80 is 12.8. Okay. Scale x and scale y. And we'll try running that. Okay, now it's still a little bit ugly because of all those dots, how it's just plotting a point. So we can fix that as well. It'd probably be nicer if they were solid lines. So we can do that by storing the old x. So, for example, if we have line 45 here, old x equals x and old y equals y. And then we can use that instead of a point command. We'll change that to the draw command, the draw line command. And use old x and old y for where the line starts. And then 2x times sx, comma y times sy. And now that'll be drawing a more solid line. Though a zigzaggy line. I don't know why the line is quite that jagged. I'd assume that there's some rounding errors going on here. We've got that done. Now, on to the actual challenge. How to implement this without a single if. How can we do this just as a mathematical equation? Now, last episode we saw a text adventure implemented with a mathematical equation from the Timex Sinclair, the ZX81. So if a whole text adventure could be done, surely this animation could be done in a somewhat similar fashion. Okay, so let's think about this a little bit. We want an equation where time goes in, and time is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Okay, and that's 10, 11, 12, 13. So, okay, so as time goes up, we want x. Now let's just think of a really simple example here where instead of width being 89, like we're doing right now, let's just make width all the way down to 3. This is what I was doing back when I used to do math contests in high school, and you're asked to do a complicated problem. I'd always try to think of a small example that was much more manageable, and extract some sort of principle from it, get some sort of pattern that could then be applied to the larger problem. So this is 4 wide from 0 to 3. So if the width is 3, time is 0. We're going to start in the top left corner again. X is 0. Now time is 1. So X would be 1, 2, 3. Then it's going to hit that right edge of the wall and start going down again. 2, 1, 0. And then I'll start bouncing up again. 1, 2, 3, 2, 1, 0. And so on. Okay, so there's a pattern here. I think we can see that every 6 steps, just going to insert some spaces here. Okay, it repeats, and then here again is another repeat. Excuse my bad Petsky art here. So we've got a pattern here where as time keeps counting up, X is going to go from 0 to 3 down again. Now, how can we simulate this with a formula? Well, the first thing we can do is just go time mod W times 2. The width is 3 here, and we multiply that by 2. We can just call that the period of the width is 6. So you see here, every time time is a multiple of 6, the X count goes back to 0 again. So just, I know we're going to use this a bit, so I'm just going to say instead of width times 2, that's going to be period width now. And this is the modulus operator, which a lot of languages have. They might use a percent sign. Unfortunately, VIC-20 Basic doesn't have that, but we can simulate that through a little equation. We'll worry about that later. So just by doing T mod PW, we've got the pattern from 0, 1, 2, 3, 4, and 5. The modulus just leaves the remainder after dividing. So this would be time divided by 6, and it returns the remainder. 0, 1, 2, 3, 4, 5. So you see here, we're actually already like halfway or more than halfway to matching this pattern. But if we were to graph this now, it would just be a dot going across the screen and then wrapping around to the left edge again. So actually, if we subtract W from each instance here, so I know this isn't real math, each one of these is its own column. If we subtract 3 from each of these, we will end up with the sequence -3, -2, -1, 0, 1, 2. Okay, now how does that help us? Well, if we take the absolute value of all of those, then we end up with the sequence 3, 2, 1, 0, 1, 2, and that is actually all the numbers that we need, but they are offset. The sequence is just out of sync. You see it's actually the 3, 2, 1 to the right here in the sequence. So to do the mod function, so A mod B is the same as A minus the integer of A divided by B times B. We can express this as X is the absolute value of T minus int of T divided by PW times PW. And now we've got almost everything except for this problem how this pattern is offset a bit. And actually we can solve that just by, in here, put an extra set of brackets, and we're going to add the width, which in our example is 3, to the input side here. So if we add the width, it actually offsets this pattern by 3 and gives us the result we want. So if I just put this into a line number here, I'm going to put that in line 20. Let's clear all that up. Okay, and then 10 for T equals 1 to 1,000. And line 5, we better define width equals 3 and PW equals W times 2. And then line 30, we're just going to print T and X, and 40, next. Let's see if we get the values back we expect. Whoops. Sorry, missed a closing bracket there. Okay, now let's try it. So, oh, sorry guys, mess today. We should start time at 0. Okay, so for time 0, we go 0, 1, 2, 3, 2, 1, 0, 1, 2, 3, 2, 1, 0, and so on. And now we can just test that at 89 and confirm that it works. So here we go. Time is counting up, and as it reaches 89 at time 90, you see it's dropping down to 88, and so on. So we've got that solved. So I'm curious if anybody comes up with a better solution, please leave it in the comments. Okay, I've put that all together in a program very similar to the previous one, but as you can see, it now has no if statements at all, and T is being incremented each step here. Let's give it a try. Again with the jaggy lines. You can see it's a little bit slower than the simple if version of it. That's not too bad. Now what's interesting about this version is that the previous version was iterative, that the current state depends on the previous state, but this version you can actually just plug any value of t in and you get the current x and y out. It isn't dependent on adding all the previous results together, the cumulative effect of all the previous results. You can just jump right in. So that means that we can skip ahead. For example, we could go ahead by a time step of 3. And you see it runs a lot faster, but it's still plotting the correct shape. But curiously, it's making the corners kind of round. And that's because the resolution of what it's plotting isn't as fine anymore. So actually we can take that to kind of a funny extreme here. Let's try time step of 9. It's really rounding the corners off. Actually has a neat style to it. Almost looks a little bit hand-drawn or something. Hand-plotted. And if we take that to a real extreme, like adding 64 at a time, actually becomes almost random because it's just drawing, well, it's not random, but it looks like scribbles because it's jumping so far in between each set of points it's plotting. So it's no longer following the actual pattern. These are all points that occur in the pattern, but the way they're connected isn't accurate anymore. Okay, fun though. Okay, thanks for watching. That's the last of the 3 VIC-20 episodes I had planned for the month of June, although I'm running a little bit late here. I think next time I'll be returning to the Commodore 128 and actually doing some 128 mode episodes. And then I've got a lot more planned. If you haven't already, please subscribe. And there's that little bell icon, and that notifies you when a new video goes live. I appreciate all the support, the comments, and all of you subscribers. Thanks very much for watching, and we'll talk to you next time. Okay, I've put that all together in a program here. Now let's try running that. Okay, I've put that all together in a program here. Let's give that a try. Okay, I've put that all together in a program.